So thanks everyone for coming today. Today I'm going to describe to you some work that we've done at NAVER LABS Europe on what we call data-driven approaches for aesthetics prediction. And I'll explain to you a bit about what that means. So Emily already gave you a bit of a run through, so I'll just very briefly go through these slides, just showing some of the services that NAVER has. So we have, for example, we have a web portal for search, which is very popular in South Korea. Also, we provide services such as mapping services, navigation, translation, many services we provide. And so at NAVER LABS Europe, so as Emily mentioned, we used to be Xerox Resource Center Europe until August of last year. And so at NAVER LABS Europe, we have research in a bunch of areas, including robotics, autonomous driving, augmented reality, user experience, and many other things I didn't mention here. So that's very briefly what we do at NAVER LABS Europe. So now I'll jump into the topic of the talk, which, as I said, is about data-driven approaches to aesthetics prediction. So this is a computer vision problem, but it's not a very typical one. Why? Because in computer vision, most prediction problems that we tackle involve fairly objective properties. By that I mean properties, so for example, for a task of object recognition, so being able to say I have an image, what kind of object's in the image, is it a person, is it a chair? This is pretty objective. Most people would agree that that's a dog, right? Same thing with semantic segmentation. So if you wanted to segment every pixel of an image and say, this pixel belongs to the chair, this pixel belongs to a car, most people would agree with you. You might have some disagreements around the edges, but in general, it's once again a very objective problem. Same thing with matching local features, etc. Most of these tasks are things that you would have a lot of consensus about the labeling, about the annotations for this task. Given that this is the case, how many of you guys are familiar with machine learning and supervised machine learning? Pretty much everybody? More? Okay, not necessarily. So for machine learning, I mean, most of you at least probably have heard of it, and that most machine learning tasks, specifically tasks related to computer vision, the ones that are, let's say, most successful, tend to involve some sort of supervision, meaning that you need a person to tell the machine what's right or what's wrong. So basically, a classic example is object recognition, where you might be familiar with Imagenet. You have a huge database of images. Each of these images have tags associated with them, saying, for example, this image is a specific type of dog, like a Chihuahua or something. And you give this two sets of information. You get the images and you get the tags. You give it to a machine learning algorithm, and that algorithm will learn to predict for you labels of unseen new images, right? But these two things are critical, not just the data, but the supervision in the form of these tags. And this paradigm of learning, of training algorithms, has been extremely successful, particularly recently with a lot of deep learning types of models. So the question we ask ourselves in this line of work is, can we take the same type of approach and use it to train models to predict more subjective properties? And in particular, we looked here at aesthetics. And so by aesthetics, I mean things like is an image visually appealing? Would somebody consider it beautiful, etc. Things where you no longer necessarily have consensus. So as I mentioned, this is sort of repeating a bit what I said. For data-driven aesthetics prediction, as for any sort of supervised learning task, you need two things, right? So you need annotated data sets, and then you also need some sort of model, right? Some effective representation for your images. We will look mostly at deep learning, but I mean, that's not the only type of model you can use. So in my talk, I'm going to describe these two things. How can we collect data? How can we collect these images and annotations for this task? And then later on, I'll describe how can we create like an effective model to represent the images and to train this model to predict aesthetics. So this is the two works that I'll describe. So this is work done with Luca Marcasotti and Florent Perronin, the first part of this work, which will describe how to collect this type of data. And then the second work with my collaborator, Albert Gordo, is about how to create an architecture, in particular a deep architecture, for learning these types of models. So let's start with the first one. So this is the problem we're trying to tackle in this case, right? I call it aesthetic prediction, and there are different types of prediction tasks you might be interested in. You might be interested in a classification task or like a categorization task, saying, for example, okay, I have these images. Is this a pretty image? Is it a nice image? Would somebody like this image? Versus, is this image not so great, not so high quality, okay? You might also be interested in not just saying a yes or no answer, not predicting just yes or no, but giving it some sort of rating, right? So saying like on a score of 1 to 10 or 1 to 5, how much would I like this image, okay? You might also be interested in some sort of distribution. So you might say, okay, you can't necessarily give an image a yes or no or a one value because it's subjective, right? There's no really such thing as just one value for this. So why don't we have some sort of range of opinions of what would sort of be like a distribution of opinion about this image? So all of these would fall under the idea of aesthetic prediction, right? But they're just sort of different types of predictions you might want to make. So as I kind of mentioned before, this is a typical machine learning or let's say data-driven based approach to tackling this problem. You start off with an image. You extract some sort of features. So you extract some kind of information from this image that should capture the relevant information about it. In this case, about what makes it nice, right? So you might imagine it might be things like, what's the color distribution of this image? How sharp is it? Is it very blurry? Where is it blurry? You know, you have to think of a way to model features that extract this type of information. Then from this, you train a model, right? So a very simple one might be a model that simply says, okay, I mean, in the simplest form, right? If the color is very bright, if there's a lot of saturation, I give it a high weight, right? If it's very blurry, maybe I lower that weight. And then this model learns to take these features to reweight them in some way, to transform them, such that it comes up with some prediction. So it says, based on these features, I'm going to predict, you know, the class, is it good or bad? Is it highly rated or not, etc. So there's been a lot of work has been done. I just give 2 references, but there's really been quite a lot of work in this area. Most of the work has been on this part. So basically trying to design ways to extract the relevant information in order to solve this problem. So what we might call feature extraction or feature design. Okay. So recently, deep models have been used to sort of do both of these at the same time, right? So for those of you who may not be so familiar with deep learning, the whole shift of deep learning is really saying, let's make this easier and let's take both of these things and try to solve it at once. And let's not try to hand design this stuff. Let's not try to think by ourselves, what do I think would make an image? What do I think are the important characteristics of an image? And try to design a feature extractor for that. But try to say, okay, let me put a model and let me just let the model learn what's important. Okay, so these are the 2 paradigms and they're interesting for different ways. But certainly recently the deep learning approach has been giving very good quantitative performance. So as I mentioned before, aesthetic appreciation is a subjective property, meaning that there's no right answer for this. So in that case, most annotations for this problem, they try to capture some sort of consensus opinion or statistic. So rather than say this is good or bad, the idea is to predict how would most people score or label this image, right? So the idea is to take some sort of collection of opinions given about an image and to predict what that is. So because of the subjectivity, training models for aesthetic prediction tends to become a large-scale problem. Large-scale in the sense of a number of images, because if you have something like, let's imagine you want to train a model to learn what a dog looks like. You can fairly quickly, with let's say like a reasonable amount of images, be able to tell what the dog is. If you want a machine to learn what makes an image nice, you can imagine that's very complex. And so you need a lot of images, you need a lot of examples to be able for it to learn such a complex concept, right? So this requires you to have a lot of images, and also you should have a lot of annotations per image, more or less for the same reason, right? So because it's subjective, let's say you had, let's say 5 people told you their opinion about an image. Statistically, that might not be, given the variance of opinion you have, 5 opinions may not be enough to really capture the full range of opinions about it. So you're going to need quite a lot of opinions to be able to say, okay, this is a pretty robust annotation for this image, okay? So given these 2 sort of main constraints for collecting data, what people have typically done in order to collect data is to crowdsource it, basically by scraping websites that tend to have this type of data, okay? So most of you are probably familiar with Flickr. So this is a Dataset. This is a website of basically a photo sharing website, right? So people can put photos on basically any topic. It's open, at least for a certain, for a limited amount of space. And people can, if you have your images open publicly to the public, people can rate your images, right? So this is one source of data. The problem with this is that it's a bit noisy, right? So when someone says, oh, they like your photo, or they give it a rating of 1 to 5, they're not necessarily saying, I think it's beautiful, or I think it's well taken. They might just be saying, oh, you know, like, oh, that was a nice birthday party, or something like that, right? So it's a bit noisy. The second source I want to mention is a website called photo.net. So this is a very interesting website because it's basically a social network of some kind, but for photographers. So it's specifically the target audience in the community is about amateur photographers who are trying to showcase their work, improve their work, have people critique their work, etc. So this is much of what we're looking for, because this is really a community of people who are trying to specifically take good photos, right? Whatever that means. DP Challenge is another one. So this is an interesting website because their community is based around challenges, as the name suggests. And really, it's devoted to having people try a bunch of new types of techniques, of styles. So for example, you might have a challenge like soft focus. So meaning that the challenge has a specific description, and I'll show you an example in a second. And you have to conform to this description, meaning you have to really try to take an image in a specific style using a specific photographic technique, okay? In this way, also, you're expected to improve your skills, and the community is encouraged to really rate each other fairly and to give them constructive feedback about how they do. So this is also a really good website for understanding you know, what makes good images, because that's really what it's designed to do, to teach people how to be good photographers. So there are several ones. I won't necessarily go into too much detail about this, but this is just to show that there are many data sets that are used in research, which have extracted data using, you know, from these types of sources. So for example, some typical ones are data sets that collected images from photo.net. There's some from Flickr, DP Challenge, etc. I'm going to talk about this data set in particular. It's called AVA, for Aesthetic Visual Analysis. So this was a large-scale data set that we collected in our team from dpchallenge.com. And I'll go to a lot of detail into that one. So as I mentioned, DP Challenge is based around challenges. So here you see an example of one. So here, the title is Skyscape, and the description is of the challenge is make the sky the subject of your photo this week, right? So the idea here is for people to take pictures of skies. It has to be of the sky. And so that implies certain types of techniques that you need to use or maybe some types of composition that you need to use to make this image beautiful, okay? And so the challenge is, you know, you have a challenge that goes on for, let's say, a week, for example. People take pictures, they submit it. People are allowed to vote during once the image has been uploaded, but they're not allowed to see the statistics of the votes until after the voting period is over, so as not to be biased. Also, I don't think you're allowed to make comments. I might be wrong, but you may not be allowed to make comments as well. And at a certain point, the statistics are tallied up, and then you have a ranking. So it's competitive. So people have first place, second place, etc. So it really motivates people to do their best and to win. And this website has a pretty active community. So on average, I think images have something on the order of, I think it's more than 100 votes per image. So it's really quite a lot. So for example, yeah, so you can see just for this challenge, there were like 136 submissions and there were 16,000 votes. So you can see it's a very popular website. And also almost 600 comments. So you can see really engaged community. Okay, so that was like the website where we collected this data. And so this is the data set that we collected. So as I mentioned, the data set consists of 255 images. So we took these images by simply going to dpchallenge.com, crawling the website, downloading all the pages, downloading the images, all the metadata to create this data set, okay? So this was like 250K images. We collected them from almost 1,000 different challenges at the time, but there are many more. Okay, so actually there are 200 votes on average, so really quite a lot of votes per image in general. And also these images come with semantic annotations as well, so they come with tags. So these tags, we get them because when a user is putting up their image, they also are allowed to tag it. So let's say you tag this image of like somebody was participating in the Skyscape challenge and they submitted their image. Once they're submitting it, they have a list of tags they can add. And so this is a list that's predefined. So it's not like Flickr, it's not like Twitter where you can tag anything you want. You have to select from a predefined list. The sad thing is that you have like a limited amount of tags. You're only allowed to tag up to 2 tags. So if you have an image with, let's say, 5 relevant tags, you won't be able to use all tags. You have to choose the 2 most relevant tags, okay? But it's still interesting information that you can also collect. We also have some style annotations, meaning that we are able to have some sort of information about the style of some of those images, simply because the images are associated with challenges, which very often are very related to a specific style. So for example, you might have challenges that are literally just about the style. So I mentioned the soft focus example. So let's imagine you have a challenge called soft focus, then you can assume that most of the images, if not all, will contain this sort of style. Or for example, you might have a challenge about taking black and white pictures, so then you can assume that it's going to be black and white, etc. So based on the title of the challenge, you can also make some assumptions about the style of the image, and also about the content sometimes. Also, we also have a lot of textual information, because as I mentioned, there are lots of comments, and these comments tend to be very focused. So you might have some comments that are sort of like, oh, great photo, but you also have many comments that say, oh, I really like the composition that you did. I really liked the color that you have. So this also allows you to have a lot of information about the content, the style, the quality of the image. So one thing to note about this data set is that it is very biased. And this is a very hard thing to tackle. And when I say bias, I mean that most of the images are what you might call mediocre. So what I'm showing here is, for all the images in the data set in AVA, I calculated the mean score that was given to it. So in AVA, most people, when you score an image, you have to give it a score between 1 and 10. And so if you average the scores that were given to a specific image by all the users, on average, people tend to get a score around 5.5, like basically somewhere in the middle of the rating scale, right? So this means that in this data set, most of the images are kind of average. So that's one thing to keep in mind, because as you would imagine, if later on you want to train this data set to predict the scores of a model, it's not going to have a lot of examples of really great images or really bad images. Most of the examples are going to be kind of okay images. So I mentioned to you that there are also semantic labels, like these types of tags. So here I'm showing you some of them. I'm showing you, I think, the 30 most popular ones. So you can see that it's also a bit biased. So for example, the most popular one is, the most popular tag that an image gets is nature, which is also by itself not the most descriptive tag. Then you have a lot of tags with black and white, some with landscape, which you might say is somewhat repetitive, because many landscape images might be only of nature scenes. Still lifes, macros, animals, and then you have like a long tail of different types of content. So one thing we wanted to look at was, we have these, what we call these score distributions, right? Because given an image, it has on average 200 scores. And we wanted to have a sense of how are these scores distributed. Is it very skewed? Do people tend to give images all the same value? How much does it vary, etc.? So what we did is we fit several distribution models. So for example, we fit a Gaussian distribution, a normal distribution, beta distributions, and some other types that we thought might be good potential candidates for these distributions. And what we found, which might not surprise you, is that the normal distribution performs pretty well for both of them, meaning that in general, images tend to have a pretty good consensus. So most people score an image around the same range. What we did find is that Gaussian distributions don't tend to model very well images that are either really good or really bad. And I'll show you what I mean by that. It's probably easier if you see some examples. So what I'm showing here is, I took all the images in AVA dataset. So this is like 250,000 images. I clustered the distributions for them into, let's say, 4 clusters here by images with a mean score that's very low, mean scores that are sort of intermediate, and mean scores that are very high. And what you see is that the distribution of the scores that an image gets, when it's really bad, it no longer looks like a normal distribution, right? It's very skewed. and the same thing when it's very high. But given that, if you recall the graph that I showed you a while ago with the normal distribution, you know that the vast majority of images fall within these, right? And there are only a few that correspond to this sort of distribution. Another thing we were interested in is the variance of the distribution. So we wanted to know how peaky this distribution was, meaning how much consensus is it? And as you might expect, and you can probably see it here, right? You can see that here the variance here is going to be very high compared to this. And you can see it here. So basically, as you move away from a mean, as you move to something that's really good or really high, the level of agreement between voters starts to decrease a little bit. So that was sort of an overview of the data set so that you have a sense of the type of data we collected. Now let me talk a bit about how we use this data in one particular application. So here in particular, we're going to learn a deep architecture for aesthetic prediction, and we're going to use this data set. So yeah, as I showed before, these are the types of tasks we want to solve for aesthetic visual analysis. And let me describe to you how we get the annotations for each of these tasks, okay? So we have, from the AVA dataset, from dbchallenge.com, we have images and we have distributions, right? So we have this distribution of scores on the order of around 200 per image that forms a distribution, okay? So if we want to train a model to predict this distribution, we can simply use this as the annotation, okay? And we can use it as a target that we want to predict, okay? If instead we want to calculate the mean, so let's say, for example, we don't really care about the variance of the opinions. Let's say we just want to know, on average, what would somebody rate this as? We can simply take this distribution, calculate the mean, and then use this as a target we want to predict, okay? Likewise, if we don't care about that and we say, okay, I just want a yes or no, is it good or not? You can threshold this and say, this image is a good image, and you can use this as your target. And then you can just train a classification model, okay? So we have different types of prediction tasks we can solve starting off from this distribution, okay, by simply summarizing it in some form. So in our case, we're interested in the last task, in the first task, the score distribution task. The reason why is because, as I just showed, we can derive all of these, let's say, the statistics or targets simply from the first. So once we have this, we can have any of these, okay? So while most works in the literature tend to focus on just binary prediction, we were very interested in finding out, what the actual distribution of scores is, okay? In particular, not just because from this you can derive other things, but because we do think it's interesting to know what the distribution is. Because, for example, you can see that for these two images, both of them have the same mean score. So both of them are considered very nice images. But you can see that this image has a bit more disagreement. So a lot of people think this is sort of like, yeah, okay, not so great, but a lot of people think it's really excellent. Whereas not a lot of people think it's really, really great, but most people are kind of like, okay, it's okay. So it's a very different type of distribution, and we think it's interesting to have this information. So there's been previous work tackling this problem. A lot of the people that have worked on it have focused mostly on features, designing features for it before the deep learning era, or they're focused on using on reweighting samples, for example, to deal with the imbalance that I mentioned. So I mentioned to you guys before the fact that the data set is very imbalanced, that most of the images are sort of mediocre. So a lot of works have focused on, okay, how can I correct for this problem, right? So that I can train a model that's better able to predict very good images or very bad images. So what we focused on with this work is designing an architecture, like a deep architecture, to tackle this problem. And so we focus mainly on how to design it and then how to train it robustly. So as I mentioned, in this work, what we want to predict are score distributions, but normalized ones. So they're actually a probability distribution. And by that, we simply mean that we take a histogram and we just normalize it so that it sums to 1, so that it's a probability distribution. Given this notation that this is a probability of an image getting a certain score, P, and G is the target probability. So G is the actual distribution that was given to it. And P is what we predict, what our model predicts, okay? We use a certain loss function. So this loss function is a function that's used very frequently for regression problems. If any of you are familiar with problems like object detection, for example, this is a very typical loss function for that. It's supposed to be very, it's been shown to be pretty robust for regression problems, especially to outliers. So we used this loss function. And in terms of the pipeline, so we designed a pipeline that's based on a very popular network for classification. For some of you might be familiar with Imagenet, so it's very successful on this data set. It's called ResNet. So what we did is something that a lot of people do with deep models, which is very often you take a deep model that was trained it was trained for classification on Imagenet. You take the weights that you have for this, and then we fine-tune it, right, for a different task. So this is something that people call domain adaptation. You can call it that. And so basically what it is that you're using basically information from a related task to better solve, like a new task, a related task, such as in this case, aesthetic prediction. So starting from this, we take these weights that we took from this other task, and then we add a few extra layers onto it to solve our particular task of aesthetic prediction. So what we do is we have an image, we apply this network to it, and then we apply some additional layers, okay? And then at the end, we're going to have a descriptor, a descriptor which will itself have a prediction layer. And at the end, the output that we get is a distribution, right? So it's just, at the end, we have a vector that's 10-dimensional. We normalize it, and that's our prediction, okay? And as I said, so we train this model using the loss function that I mentioned before. So one thing I want to mention is that as you might imagine, the aesthetics of an image is related to the content that's in it, right? By this I mean, for example, if you take an image using a certain style, a certain photographic style, it's going to be appropriate or not depending on the content in the image, okay? So for example, if you take what we call a macro, so a macro is this type of style where you have like an object very focused in the front, in the foreground, and then the background is sort of very blurry. This will work really well for a lot of nature photos, and so you tend to see nature photos that look like this. But for example, if you try to do this style with a landscape image, it wouldn't work, right? So the point is that there's a relationship between the content and the aesthetic properties of the image. And what we wanted to do is to take advantage of this to train a model that's more effective. So to do this, we had to think of an interesting way to do it because it's not so clear how to leverage this type of information. An obvious thing you might think of is to say, I have this image, I have annotations about the image, for example, the distribution I have of scores, and then if, for example, I also knew the content of the image, you could leverage this very directly, right? You can say, okay, this image has, I know it has a dog in it, I know it has an animal, etc. And you can take this data and you can plug it in somewhere into your model, okay? The problem is that most data sets don't have both types of information. So I mentioned to you that AVA has semantic annotations, it has these tags. The problem is that they're what you might call incomplete, in the sense that given that you're only able to give at most 2 tags, you have what you might call false negatives. So for example, you might have an image where the tag, food might be relevant, but because you were more interested in putting like still life or black and white, you weren't able to tag it with food as well. So that means that if you want to use these annotations, you might falsely say that, okay, this image is not relevant for a specific class when it actually is, okay? So that makes it difficult to use the annotations that AVA has. So what we try to do is use an approach that's inspired by what's called model distillation. In a nutshell, what model distillation does is it tries to say, okay, let me take a network, a deep network, and usually, that's been trained for a specific task, and assuming it's very good at this task, I can take its outputs and treat it as if it's annotations, okay? So what we did in this case is we took a model that was trained on Imagenet. So for those of you who are not aware, Imagenet is a data set of, there are 2 sizes of it, and the one that's typically used has 1,000 classes. So these 1,000 classes are usually enough to cover, a pretty broad amount of types of of objects you might be interested in. And so what we did is we took our AVA images, we ran it through this network, we took the classes that it were annotated as, like the predictions from this network, and we treated that as true labels, basically. So basically, we sort of collected labels using this network that we assume is doing a good job. Okay. So what we did with this is we took this data, and then we did what we call multitask learning, which is we took our network for aesthetic prediction, and we added in a new task. So we said, okay, this network has to not only be able to predict if an image is nice or not, etc., to predict the distribution, it also has to predict these labels, okay? And one last trick we did is that rather than collect the labels themselves, because of course there's going to be a bit of noise, what we decided to do was to collect the probability distribution over the labels. So as I mentioned, in Imagenet, there are 1,000 labels. So there are things like bus, car, dog, cat, etc. There are these types of labels, and there are 1,000 of them. And so we figured that rather than trying to just extract one, the most likely one, which could be wrong, instead we said, okay, what's the distribution over all these labels? Because in that sense, even if it's wrong, it's still fairly predictive. It gives you a good idea about what semantically the image looks like, okay? So what we did is we said, okay, we have these new kinds of labels, right, which is these probability distribution over semantic classes. We have the distribution over aesthetic labels, and we wanted the network to learn both of them, okay? Because the idea is that if one model has to learn those two tasks, then the model itself is going to absorb information about the two types. So it's going to have to be able to represent not only what's aesthetically nice about the image, but also what is in the image semantically, okay? And in doing so, it's going to be able to leverage semantic information. So this is basically what I explained to you, but like in graphical form. So as I mentioned, you take input images, you get this 1,000-dimensional output, okay, which we call, like, it uses softmax to get a distribution. As I mentioned, so we train our network to solve this task. And then we also train it to solve our aesthetic final task, okay? And so now I move to some experiments just to validate, how all this stuff worked. So as I mentioned, we use the AVA dataset. So this is the dataset I described before in the first part of the talk. And this dataset has 20,000 images that we use to validate it. So we use it as a holdout set. And the rest of the images, or about 230,000, we use for training. And we evaluated it on 3 tasks. So the 3 tasks I've been mentioning. So predicting a distribution, predicting a mean score, and predicting a yes/no, like binary classification task. Okay, so here are some experiments. I won't go into so much detail on everything. I just want to describe, for example, these are the metrics that we used. So one is scale divergence. So this is a metric to measure the difference between 2 probability distributions. So the lower it is, the better, because it's a distance. This is the same. It also measures the distance between 2 distributions. So we use this to measure the first task, right? To see how close is our predicted score distribution to the actual one, okay? Here, this is mean squared error, and this is Pearson's correlation coefficient. So these two are used to measure the difference between the mean score that we calculate from the distribution and the target score. And then here we have classification accuracy, right? So these are for the 3 different. So what we can see is that, first of all, so our method, which we call AVA-DIS, and there are different versions of them, but this one performs best. And then another thing that's interesting to note is that these two show the difference between not using semantic information and then using semantic information. So here we can say we get a small improvement, particularly when we want to compute mean scores from leveraging semantic information in this way. And here we just compare to some state-of-the-art work. So these are other works in the literature that have solved these problems. And once again, we outperform them quite a bit. And then the nice thing is that with our method, because we solve the fundamental task of predicting the distribution, we can solve all 3 tasks, so distribution prediction, mean score prediction, and also classification, while most works tend to focus on just 1 or 2 out of the 3 tasks. So here I'm showing some qualitative results. So what we did here is, if I remember correctly, we took all the images in the testing set, we ranked them based on the mean score, and here we're showing you the top images based on our ranking, and the bottom ones based on our ranking. And then we're showing you the difference between the distribution that we predicted and the actual one, okay? So you can see that the distributions that we predict, that they're in the green, they're not too bad. You can see that these images at least look pretty nice. You can see that these images are not so nice. So this is what I mean by images that get a low score. One thing that's interesting that you can see, if you notice, is that the predictions tend to be pretty similar. So if you look at these green, you can see that they're almost the same, right? They're not exactly the same, but they're very similar. So you can see that our model is learning almost a kind of template, a fine-grained one, but a template nonetheless, for images of different levels of quality. So we definitely have failure cases. In general, when we have images that are really, really good or really, really bad, it tends to not do so well, which is normal because, as I mentioned before, there's this huge bias in the data set, right? The data set really does not see stuff like this very often, and so is not able to really learn to predict it. So this is something that we really wanted to figure out how to solve, but we haven't tackled it yet. Other people have worked on this problem. Most of the methods that work on it manage to do a little bit better here, but then they perform worse on the images that are like average, so it doesn't really work out. So the last thing I want to mention is working on interpretability, because especially for aesthetics, a lot of people care not just about is it nice or not, or how nice is it, but really why, right? People want to know why is this image nice, like which characteristics of the image make it good or bad. Once again, a lot of people have done work on interpretability of machine learning models. And it's easy to interpret a model when you know exactly what features you're using, right? So if you, in the past where people use a lot of handcrafted features, you could easily say, okay, I know that this feature vector is modeling saturation, or I know it's modeling sharpness, for example. And so you can say, okay, if these features have a high weight or a low weight, then you can say that, okay, I know that this image is sort of not good, or it's not performing well in this aspect versus another. When you have a deep model, it's like, you have no idea why you're getting the results you're getting, okay? So this is a problem that's not just for aesthetics, it's for deep models in general. And so a lot of works have tried to interpret deep models, particularly, for example, by visualizing the weights that it learns. So those of you who know about deep models for vision problems know that very often you have convolutional filters. And if you visualize them, or at least visualize what tends to activate them very well, you can have a sense of, okay, these types of patterns are very important. But you can imagine for aesthetics, that's not really going to work so well. So what we propose is what we call an adversarial approach. So what we try to do is to say, okay, I have an image with a certain score. If I wanted to make it better or worse, where would I need to change? Which regions of the image would I need to change in order to do that? So here I'm just going to show you some qualitative results. So what we did basically is we took an image, we took its score distribution, we changed it to either make it like a better distribution or a worse one, meaning that it's more shifted towards the high end or the low end. And then we backpropagated this through the network to understand which regions of the image are being changed the most in order to make the shift valid, okay? So what we can see, and these are some examples we found. Honestly, this is, it's not always easy, you don't always get a very clear signal, but we did find that very often it focused on foreground objects. So for example, you see here, it focuses on the face quite a bit, focuses on these very sharp regions of the image. And then also we saw it was a bit biased towards the face, which we think is a bit of a holdover, because you can see it's biased both for the horse and the person. And we think that this is probably a holdover of the fact that our model was initially trained on Imagenet. And in Imagenet, animals and people are very prominent, and they're very important to be able to understand the content. And so the network is a bit biased towards content of this kind. And so to summarize, to wrap up, I discussed two aspects of machine learning for this task. So I said that, the question we asked ourselves at the beginning was, can deep models learn something as subjective as is this image nice or not, right? What do people think about it? And we found that yes, that's the case. Once you have a data set that's big enough, once you have representations that are powerful enough, okay? So some challenges, I mentioned them before. As I said, most images are average. So this means that even though I think our method is pretty good at saying whether a good image is good or a bad image is bad, it's not going to be very fine-grained about it. So if you want an image that's a 10 out of 10 versus one that's an 8 out of 10, it's not going to be able to make these types of distinctions. Also, the semantic content is also biased. So as you guys saw in the plot I showed of the histogram of the tags, the most common tags are all, as I said, so like nature stuff. So there's not a lot of, the content itself is not very varied. And then also another thing is that, so we took this data from a pretty particular community. So this is a community of photographers who, they're very professional, they have their own way of doing things, and you could say that it's just something that may depend on the community, might depend on the culture. So maybe if you took a community that wasn't very like American, you might get a very different type of style. So you might ask yourself, okay, if I took my model and I trained it on images from South Korea, would it do really well? It's not so clear. So that's it. I want to make a brief plug, basically, for an AI school that we're hosting in Grenoble. So it's called PISS. It's going to be a really great summer school that's being co-hosted by NAVER Labs and INRIA. And there are people, there are like amazing speakers like Yann Lecan, Ken Young Cho, Igor La Rochelle, Andrew Zisselman, really great people in computer vision, NLP, machine learning, etc. So if you're interested or know anybody who's interested, the deadline to apply is April 4th. And one last plug. So NAVER Labs Europe is hiring. So once again, we're hiring researchers, engineers across all levels of experience. So if you're interested, don't feel shy. Feel free to reach out, to go to our website to learn more, or to reach out to dlcandidates@naverlabs.com. And that's it. Thank you so much for listening. Any questions?
I was curious about the teacher-student models. Did you consider transfer learning?
So what we would do, I would consider it. So we definitely do. There's definitely a lot of elements of transfer learning in everything that we mentioned. So I mentioned domain adaptation, which is itself a type of transfer learning, right? And I mean, I would say that this is transfer learning because basically you do have information from another task that you're trying to use in this new task, right? So basically you literally have the output of the predictions of the semantic model that you're using to bias the weights of your model for this new task, right?
But the idea of transfer learning is to have the weights preset so that you learn faster. So is it because you wanted to have another internal representation?
No, I would say transfer learning is way broader than that. For me, transfer learning is really, it's knowledge transfer. So, there are specific instances of that where, for example, you might want to, fix your certain weights and then learn new ones on top of it. What people have tend to find, and there was a paper in NIPS 2014 that showed this, which is that you can do different things. So you can take a network that you learned on one task, you can fix the weights, don't change them, and you can add new weights on top of it, right, to solve a new task. Or you can take those same weights, and you can fine-tune it. So you can sort of relearn on top of that, right, which is what we did. And this is very standard, and it works very well.
Has some work been done in aesthetic prediction using unsupervised learning, or do you think it's even possible?
I don't think there has been anything that's been done. I am not aware of any work that's been done using unsupervised learning for this. Because this is such a human thing, right? Without supervision, what does it even mean, right? For something to be, So I couldn't think of that. If you can, I'd be interested. But as far as I know, no.
Well, I have one question. It's most related to the end of your talk. You talked about how to analyze the deep neural network.
Mm-hmm.
And the problem is very difficult, it's very subjective. So my question is, at the end, do you have some conclusion if at the end the classification of the image or the ranking of the image is more related to semantics, or to the object, or is more related to low-level features like brightness, contrast, and so on?
I think it's related to, I don't think I think it's more related to what you might call low-level properties. And then also things that are not so low-level, but things that are more abstract, like composition, I think is very important. So where, how do you actually compose all the items in the image? That tends to be a very big cue. Then also, yes, low-level stuff like brightness, etc., is also very important. And content, I think it's less so, but it also definitely plays a part. Yeah. I think they're all important in various ways. Yeah.
Do you think your model was able to learn if a given composition is good or bad?
I would say yes. So one thing I didn't mention here in the talk is that we do incorporate a kind of prior knowledge about composition in the way we created the architecture. So when you saw this sort of architecture that I showed with all the different layers, right? At a certain point, we put in what we call it a spatial pyramid, but basically it's like a grid where we take features from a predefined grid. So for example, we take the image, we divide it into a 3x3 grid, and then we take information from each cell of the grid, and we treat it differently. So basically what we're doing is we're not shoving every part of the image into one representation. We're creating like a representation for every region of the area in the image. And so that gives you some rough information about not just what's in the image, but where is it in the image. And that gave a boost. So definitely knowing a little bit about the composition is helping somewhat. So I wouldn't say it's necessarily very fine-grained. I'm not sure if it's semantic, meaning I'm not sure if the information that the model captures is something as semantic as, if a person's in the top left, it's good, etc. But I mean, there is some information about the composition that's being captured. Thank you.